Hello everyone, my name is Gang from Google Research. Today I'm going to present our work learning to denoise raw mobile UI layouts for improving dataset at scale. This is a joint work with my colleagues Gilles, Manuel, and Yang. So mobile UI layout is a tree structure describing the objects on the UI. Here we show a few examples of screenshots and their corresponding UI layouts. We can see the bounding boxes from the UI layouts roughly match the objects on the screenshot. UI layout is critical data for many machine learning tasks, including screen parsing, icon annotation, and widget captioning. The motivation of our work is UI layouts are often noisy because they are automatically generated by the mobile operating system. And our question is, can we denoise the layout automatically? We first into UI layout dataset and identify two main issues. The first one is invalid objects. This includes invisible objects. For example, on the right side, we can see this bounding box doesn't have any object in it, so it's an invisible object. It also includes objects with mismatched bounding boxes and objects in background which cannot be clicked. The second issue is generic or app-specific object type, like view linear layout, which is very generic and doesn't contain much information, or Columbia native add view, which is too app specific. These two issues will cause problems when the UI layouts are used as input signals or output labels. For example, when used as input signals, the invalid objects result in wrong visual features because their bounding boxes are wrong. When used as output labels, the invalid objects will be wrong labels to object detection models. The generic object types might include semantically different types, which might confuse the models. In this work, we propose a two-stage pipeline to denoise the layout. So first, we have the noisy raw UI layout as input. In the first stage, we try to detect and remove invalid object. In the second stage, we do object type recognition and assign semantically meaningful types to the valid objects. And finally, we hope to obtain a clean version of UI layout. Our previous work used heuristics for object type recognition, which is difficult for scaling up. Because there's no existing dataset, we first create a dataset for our task. We use the Rico dataset, our foundation for labeling, and we pre-process the layouts to remove examples with too few objects and also remove invisible occluded duplicate objects. After labeling, we do app-wise split to avoid information leak for model training, and we split the dataset into training, validation, and test set. In total, we have around 60K screens labeled with more than 1 million objects. Here shows the collected label distribution. The common object types include text, container, pictogram, and also invalid objects. The rare types include date picker and map. For invalid object detection, we treat it as a binary classification problem and use ResNet to solve this problem. So first, we input the original RGB channel into the ResNet, and we use the fourth channel to indicate the location of the current object of interest. And we input all the 4 channels into the ResNet to generate a feature vector, which will be passed into the dense layer for the final prediction. For object type recognition, we treat it as a multi-class classification problem. We investigate 2 model architectures, graph neural network, which will encode the layout hierarchy explicitly, and transformer, which will encode the layout via self-attention among the flattened nodes. For comparison, we also have a heuristic baseline, which will decide the object type based on information like resource ID and Android class name. For example, if the resource ID is navigation bar background, then we can say this is a navigation bar object. For the GNN model, we first encode the nodes in the UI layout into a dense vector using nodes attributes, including text, content description, Android class. For the pixel information, we crop out the pixel of the object from the original screenshot and encode it with a ResNet into a dense vector. Then we concatenate these two dense vectors into one and pass all the dense vectors of the objects through the graph neural network, which will generate the final representation of the object for the prediction. For the transformer, the node encoding in the UI layout is similar. The difference is that for the screenshot, we encode the entire screenshot using a ResNet and a transformer encoder, and we communicate the pixel information using cross-attention between the node embedding and the pixel embedding. And the transformer decoder will generate a final representation for each object for the prediction. We evaluate all our models on the test set. For the invalid object detection, we obtain about 82% F-score with balanced precision and recall. For object type recognition, both GNN and transformer model achieve about 86% F1, significantly higher than the heuristic baseline. We did a few error analysis to understand why the model make the mistakes. For invalid object detection, we sample 100 false positive cases and 100 false negative cases, and we found that the main error cause is the object with slightly shifted bounding boxes. For example, this object, human labeled it as valid, but model predicted as invalid. This is ambiguous because in our guideline, we specify the invalid object as those with mismatch bounding boxes. And there's some uncertainty of how much mismatch we allow the object to be valid. For object type recognition, we sample up to 50 instances for the 5 most common confusions, and we find that the main cause of the error is the ambiguity due to similar looking objects. For example, the first example, the ground truth is button, but the model predicted as text because it looks like a text element, but actually user can click it and result in an action on the screen. For the second example, the ground truth is image, but the model predicted as pictogram because it looks like an icon. For conclusions, we identified 2 main issues of noise in mobile UI layouts, and we propose a 2-stage solution for layout denoising by first detect and remove invalid objects, and then assign semantically meaningful type to valid objects. We created a large dataset for model training and evaluation. Thank you.